We continue to write the compiler for the unary programming language, and today we are going to begin with the introducing of an additional keyword. I want to be able to write nil instead of 0. So there is actually no type system, so the only type that we have is word. But I want to have not only 0, a lot of words are pointers, and I want to be able to assign a nil to a pointer instead of 0. We are going to introduce a keyword nil, and it will be just converted to a 0 later. Probably we will write the code twice. So this is a multi-stage compiler where we write the compiler in itself, and it only supports the features that are already implemented. And we are currently on stage 16 of our compiler, and to be able to write nil in stage 16, we also need to support it in the previous stage. So in the 15th stage, and we can also create a new stage, the stage 17, but I don't want to create a new stage because of such a simple feature. I think that I already have a token for nil, and it is called null. I have chosen null because nil is a keyword, so we can't use it as identifier. So I use null as identifier, since it is not a keyword in our programming language. And if we look for null here, exactly, so it is a part of our Alexa. It gets an identifier, and it just checks whether this identifier is a keyword, and here it checks if it is nil, and if it is nil, then we assign null to this token as its kind. So it is already supported in the Alexa. I'm going to split the screen, and I will open stage 15 in the top half of the screen. So it is boot stage 15 CLL. I hope that I added nil here. Yes, that's fine. So the next step would be to add a node for the nil, and we just going to add a new node to our abstract syntax tree. Records are new in the stage 16, so there are no records in the stage 15. Let us call it just null. It's actually nil node record, and the only thing that is part of this node is its kind. So we write it here, and to implement it in the previous stage we need to define 2 or 3 functions, probably only one. We can actually use just this this node function since it's actually everything that is supported by the null pointer. So we do not need to do anything here. Then we have three nodes, so there should be somewhere a list of all possible nodes. I think it is actually node kind, and here we need a new kind. It is null. For the same reason, so null is a keyword, so we use basically just null here, and we add null also here. We can check if it compiles. It does. Now we need to parse this thing. It is handled similarly to the integer node, so we can just look where we parse in integer literals. And it will do basically the same. So let us define a new procedure, parser nil. If we entered this procedure, then we already know that the current token is a nil token, so we just need to skip this token here. Then we need to allocate some space for this token, so it will be called result, and we can just allocate it. It will be, what was it? I think nil size, and we need to set the kind of this node, so it will be basically nil node set kind. And this one is of course node size set kind. For result it was another kind null. Kind but not kind. Exactly, so we created a node and we need to return this. And we are actually want to do the same in the previous stage, so we look for the same parse function. It will be a bit different. So we basically create a new function, a new procedure with the same name. So it's parser nil, begin and end. We need a variable result. We can't use malloc in this stage yet, so I had a different allocation function, and we define a new variable literal size, and we assign the node size to this variable, so it basically would be node size. I hope such a procedure exists. It doesn't. Yeah, let us define nil node size and it just returns 4. So the record just has the kind element, so and all data types are 4-byte loans, so we return basically 4 bytes because it's a single field. We don't need to store any additional information. Nil node size. Then we can allocate memory with the allocate procedure, literal size, and it's almost that, so we can just assign node set kind to the result. This is the same node kind null, and then we return this thing and hope that it compiles. Now we need to use this function, so we'll just look there where this literal is used. Parser integer literal, and we just need to add an additional condition here, so we just check probably before, else if token kind is Alexa kind null, then parser node is Elna parser nil. That's it. And the same in the 15 stage. Now we can parse nil, and the only remaining thing is to convert it to a 0 then when the code is lowered to the intermediate representation. So we can just look where node kind integer, where this one used. Exactly, this is the function we are looking for. So it converts a simple expression, basically it is literal or a variable name, it converts it to the 3 address code. And we have here a conversion function, for example, unary integer literal, and we just define a similar function here. So it will be prots unary nil, and the argument will be just this nil node, and everything it should do is just create an immediate value in the register T0, the value nil, of length nil, and the same here. The literal TAC. Here it will be a bit different actually. So in the 16th stage, in the current stage, we don't write the values right away into registers, but we pass them further, but it's actually very similar, so the procedure will have the same name, unary nil, and this is nil node. We don't need the node actually, it doesn't have anything interesting for us, but we do the same. We get 3 arguments here, and we just say that the value is an immediate and its value is 0 and its length is 0, and we return also 0. This is for it. We compile it. So, and there was this simple expression function, I think it was this one, and it basically checks what node it gets, and we need an additional check here, probably after this integer literal. We just check if the node kind is not kind null, then the instruction is generated with the unary nil function, and we do a similar thing here. We look for this simple expression, and we add an additional condition here. We check for the type, but it gets additional arguments, so it can save the return value. That's it actually. So it compiles, I think, and we just need, actually I've seen that integer literal returns 0, and it's not really a 0, it's a nil. But it doesn't work. Let us check, or I do an additional test, maybe not in the return statement, but in assignment. Pattern node, that looks like a pointer. Yeah. So let us check again. So if we see this, if we see nil identifier, then we say that it is Elna Lexakind null, and Elna Lexakind is available in here. Yes, it is in here. Actually, I want to see where it fails. Save the current progress, and then we find a place where we can replace the nil, the 0 with the nil. And now we do it once again. Stage 14, 15. And we try to compile the 16th stage, I think, with the 15th. So we look into the build directory, into valid, and stage 16. It doesn't exist. And boot stage 16, it exists, but it is empty. So it would mean that the 15th stage crashes during generating the 16th stage, I suppose. Valid stage 15 should be available. Let us run it in the debugger. So we want to run this code and pass the stage 16 source file to it and see what happens. If I just do run, then it hangs. Yeah, it actually works and exits normally, but the generated assembly isn't what we expect. It shouldn't end with this empty ASCII string. Okay. So stage 15 generates wrong code somewhere. Actually, let us look where integer literal is used, so probably we have forgotten the handling somewhere. This is the size of the node, literal node size. Okay. So this is the parser result. We allocate some space, set the kind, node set kind. So during the parsing, I've forgotten to skip the token after seeing it. So the nil token, I added the call to this function, to the skip token function in the stage 16, but not in the stage 15. So now it works. We can use nil in our source code, and we need to adjust the comment here. So at the top of the file of each stage, I write the list of features that are implemented in this stage and that can be used by the next stage of the compiler. So we just add nil literal in here, and now we are basically done with this feature. And once again, I'm going to save my progress, so we just look what has changed, basically both stages. So we just add boot, and now we can continue with the stage 16. Another thing that should be improved is the handling of the unary expressions. It's basically the last thing that should be, not the last thing, but the generation of the free address code should be improved here definitely. We did similar changes for the other kinds of nodes, but not for unary expressions. And the actual problem, so I think that I have only two unary operators currently. It is the minus and not. And if you look how these operators are handled, then I expect, so the first operand is the target operand, it's where the result is saved, and the second operand is the source, so it is the operand to apply the unary operation. And what it basically does, it uses the same temporary variable, so 6 is the number of the temporary variable. It's converted later to the T0 register in the RISC-V. So basically minus looks like minus t0, but it actually expects that the previous operations, for example, if I have if I want to negate, let us say 1, then it expects that 1 is saved in t0, and then I can negate this. But this is actually too low level for the intermediate representation, so it just should support -1. So I think actually that not isn't used anywhere. Yeah, I don't use it, but minus is definitely used. This handled actually here if the value that we get, if this value isn't an address, so if it isn't a variable, then we copy this value into this 6th register, and with other change it should be possible to skip this step basically. So it should be possible just to remove this whole block. It will crash now. This is expected. Actually, we can look at the diff. Yeah, so I will split the screen again, and we go to the handling of the unary operations. So we need the function, the procedure that compiles our 3 address code, our intermediate representation, and into the next pass of the compiler, into the RTL or assembly. This function is called RTL instruction theoretically. And it is basically this this procedure. So we check here our instructions, and somewhere we should handle the negate instruction, I suppose. And it is basically, so this is the place where the intermediate representation of negate is converted to the assembly, and it just copies this thing exactly as it is given in the intermediate representation. But actually what we want to do, we want to add the value from the source. I think it was the load operand value procedure, but I don't know what arguments do I need. I think it was TIC instruction, and the second argument was load operand value. Exactly, the second argument is the operand number, I think, so we need the first load operand for store. I think that this should be the second one. Yeah, it should be the second one. So we need to load the second argument into the register T0. This is actually fine, but it is the wrong instruction. Into RTL register T0, we get the instruction that does this loading, and we need to create another instruction, the negation instruction itself. We save it into the next instruction variable. RTL instruction set operand, yeah. RTL the target remains, but the second operand would be basically set instruction RTL instruction set operand TIC instruction 2, and the operand is basically RTL operand register, and this register is register T0. So this is the source, and the one remaining thing, we should set the next this procedure returns a list of instructions, and the first instruction in this list is result, the conversion of the source operand to the RTL, and basically we need to say that an instruction list set next, and the first instruction is result, and the second one is basically this next instruction. And it gives us the same error still, which is a bit disappointing. Instruction is set next. We copy the first operand and we set the second operand to a register. Won't have any effect, probably. Yeah, we still get the same error. And there is nothing to wonder about. So basically, of course, we still expect here that 0 register, but we should replace these values with operand type, operand value und operand length. So it seems that later there is some code that still expects that the variable is saved in T0, but if we check for the operator, so it's actually wrong. Actually, I say that exactly if it's not minus, so if there is no operator, then we load this value into T0 because some code later expects it, but actually our unary expression works, so we can just do an else if out of this thing, and we can remove this and here. So we should look at the other places that use unary expression, because some of them still expect that these operators are saved, and I basically think that procedure call may still require that the immediates and such are saved in this T0 register. We should look at them later, but at least for the unary operators we have fixed this so that the operand doesn't expect the value in the temporary, but it accepts any supported operand type. So it is not only a register but also an immediate or stack variable or something like this. The one thing that we want to do, so there are basically multiple unary operators, and I think that we can unify the handling a bit. So we are go to this procedure. This is the line 1143, and we define a new procedure because this procedure is already a bit longer than it should be. So we define a new procedure, RTL unary, and we get the DAC instruction, and we basically just copy the code already written from here into here. And then another thing that we need this RTL operator. So we get it as argument, RTL operator, and we use RTL. We need a few variables. Probably next expression can be passed as an argument as well. So just next instruction is a word, and we return the result at the end. So operator negate is the RTL operator, and then we can reuse this procedure then when we handle unary operators. So we basically say that result equals to elna RTL unary, DAC instruction as is. The operator in this case is RTL operator neg, and that's it, I think. We put a comment around it at first, and we'll try to compile it. No, this is wrong. Of course, I've forgotten the next instruction. I haven't defined result. Yes, I've forgotten the local variables. I think the only one that we need is this result variable. And that works. So we can remove this. And we need to add similar handling for the not instruction. So we just write not here, and we can remove the old code. And this compiles too. And I think that we will finish here for today. So we implement two small things. So the one is the nil value, or nil literal for the null pointers, or nil pointers in this case. And we did a small improvement to the intermediate representation of a unary expressions, and we will continue later, I suppose.